Hello everybody, this is Guy Darmus. In the last video we did some freefall experiments with lead and zinc. This time we want to try rubber and zinc, for which the difference is much greater. We can calculate the difference like this. 2 times the height here in meters divided by the free fall acceleration, and here we multiply the free fall acceleration with the ratio between the g-value of rubber and the g-value of zinc, and we can calculate that g-value by multiplying the g-value of hydrogen with this ratio here. So ratio between the gravitational mass and the inertial mass. So here we have 5 times the gravitational mass of carbon, which is here the number of protons in carbon multiplied by the mass of the proton in atomic units, and added to that the number of neutrons in carbon times the mass of the neutron in atomic units. Then we do the same for hydrogen, and you may think that with hydrogen it's very simple, but so you have to account for all the isotopes and to be very precise. That's why it's not just a single proton. Here you have 5 times the mass of carbon plus 8 times the mass of hydrogen. And that's what you get, 6.659 something. And that's pretty low if you compare that with iron. Iron is 6.67428 according to my research. And yeah, so that's the math. And here, that's a pretty big time difference, the biggest you can get. And I mean, of course, it would be much bigger if you could just drop hydrogen, but hydrogen is the gas, so you can't really drop that. But it's very good that there are so many compounds where there's hydrogen in it, or oxygen, so that brings the G values to a very low point. Something I didn't explain last time, and some people think I should explain it more clearly, is how this thing works. Is the ball falls through the first footer gate, so it starts counting, and then when it passes the second footer gate, it stops counting. So here it took a long time for my hand to travel there, so that's why. That's the time there, 3 something seconds. So this is a rubber ball inside this vending machine ball to make sure the size is exactly the same. So let's start. Make sure that it is precisely centered, which it is now. I'm gonna press this release button. So this is falling much slower. 6016, and we record everything here. 6016. And now zinc. Six 001. Now I've tried out rubber in my original experiments in 2023, and I did experience it falling a bit slower than predicted. Could have to do with the fact that it's so elastic, so the air might stop it more than normally. So at least this doesn't play any role for all the other materials, but for this it does. 6012. But let's see. Who knows? Maybe we get somewhat close to the predicted difference. So this is quite interesting because we don't know what exactly is going to happen here. $6001 again, but it's always nice to get such small standard deviations. And again, to explain, the difference in the freefall times is due to the fact that the elements further down in the periodic table, they have more binding energy, and that binding energy is negative, and since mass is a form of energy, it reduces the mass but not the number of particles, and in my theory it's the number of particles that gravity depends on. What was the value here? 615. And so then you have more gravity per kilogram or per gram or whatever the mass unit is. For sure, the standard deviations are not going to overlap this time with such a big difference. The tape that I use here this time is for reducing the magnetism a little bit, because the content is much lighter. The balls from last time were very heavy, and so they tend to stick to the magnet when they are very light. So they would fail to drop because the magnet is switched off just for a moment, and if the magnetism is too strong, then the release fails. $6005. $6004. Well, 11 microseconds, that's a bit too much. But well, we predict 7, so who knows, maybe there's more hydrogen in this rubber ball. $16. there are many more materials we can use later on, though their differences are smaller, so it's less interesting, but maybe still interesting because we want to know if the predicted difference is what we observe. But as I said, with rubber balls, they have this elasticity which these other materials don't have, and they can cause quite some deviation. 6006. I don't want to make this video too long, so I'm not too careful with placing it exactly in the middle. Just somewhat careful. 615. As you can see, the zinc sphere is always faster. So basically now we're just interested in the time difference here. Six, four, again. Six, 17. But yeah, you pretty much get the picture. It's difference is more because the elasticity involved here. 614. It's just normally I alternate between the two, but in order to make sure that the distance is the same every time, but yeah, for getting the video done a bit quicker, I'll just finish the trials separately. Six 21. That's an outliner. We're gonna do that again. $6.15. And now I'm gonna finish up the zinc trials. Well, 10 trials of any experiment is pretty good. 6006. Six 4. And one last trial. Six 005. Okay, and so as you can see, the standard deviations are not overlapping. and this is the time difference. Now let's see how it changes if we're looking at a smaller sample, let's say here, and here. Well, it's still pretty big, yeah. So that's basically because of the elasticity of this sphere. The distribution of the mass plays a bigger role only if you're rolling it down. The reasons for that are quite complicated. Has to do with the fact that you have the different parts of the mass rotating, but here nothing is rotating, it's just falling straight down. So the only thing that can explain the difference is the elasticity. Yeah, in 2023 I was also thinking about if it can make any difference if light shines through, like when something's half empty, but that's very difficult. I mean, would be scattered all over the place, so I pretty much disregard this possibility. Yeah, so next time we're going to do some trials with aluminum. That's this here, this aluminum, and this is iron, and this is wolfram. That's very, very, very heavy. So yeah, it would be hard to find a pair for this one. Yeah, so that's all for now. See you.